I've used the word dimension in a couple of examples previously in 0007 when we talked about the plane being two-dimensional space, or the R cubed being three-dimensional space. In this video, we're going to extend the idea of dimension to arbitrary vector spaces. The way we'd like to do this is by thinking of the dimension of a vector space as the size of a basis of that vector space. But there's a problem in doing that. We know that every vector space, except the zero vector space, has many different bases. So perhaps there is a vector space which has bases of two different sizes. In order to use the size of a basis as the definition of dimension, we need to ensure that doesn't happen. And this is the main lemma which we need to prove this. It's called the Steinitz exchange lemma, and I've actually called it a theorem here because it's really a difficult and an interesting result. Here's what it says. You take a vector space V. You suppose that you've got a spanning sequence S1 up to Sm for V. You then take any linearly independent sequence L1 up to Ln of V. The conclusion of the theorem is that m is greater than or equal to n. In other words, the size of any spanning sequence is greater than or equal to the size of any linearly independent sequence. Here's how the proof goes. Since S1 up to Sm is a spanning sequence, we can write absolutely every element of V as a linear combination of S1 up to Sm. So we're going to assume for a contradiction that we've got a spanning sequence which is smaller than a linearly independent sequence, and we're going to write each element of that linearly independent sequence as a linear combination of our spanning sequence. And we're going to record the coefficients that it takes to do that. So for each j, we will choose some scalars a1j up to amj, which express lj as a linear combination of S1 up to Sm, and we'll write those scalars down in a matrix capital A. Let's draw this matrix so we're sure what's happening. The matrix would look like A11 down to AM1, that will be the first column, and those will be the scalars which told you one way of expressing L1 as a linear combination of S1 up to Sm. The next column, A12 down to AM2, would tell you how to express L2 as a linear combination of S1 down to Sm, and so on. And let's make this nice and wide because we are assuming for our contradiction that the matrix has more columns than it does rows. So this is our matrix A. And the meaning of A is that the jth column is telling you one way to express Lj as a linear combination of S1 down to Sm. You'll see that it's got n rows and m columns, and the m is less than n, so it is wider than it is tall. So what does it mean that A has more columns than rows? Well, one of the things this tells us is that the matrix equation Ax equals 0 has a non-zero solution. If you imagine taking the augmented matrix for this matrix equation and putting it into row-reduced echelon form, because A has more columns than rows, that means that not every column in the first part of the matrix can have a leading entry. So there must be a column with no leading entry, which means there is a solution parameter which can be chosen freely. And in particular, there are non-zero solutions because you can choose one of the variables to be non-zero. So let's fix notation for a particular non-zero solution. Any of them will do. We'll call it V, and V will be a matrix, a column vector, which looks like V1 down to Vn, like this. And V has the property that A times V is equal to the zero vector. Now I claim that the coefficients of V give a linear dependence relation on the supposedly linearly independent sequence L1 up to Ln, which will give us the contradiction we want. So let's examine why that's true in this third bullet point. We start off by thinking about this linear combination V1 L1 plus V2 L2 up to Vn Ln. Now we're going to substitute for Lj. Remember, we wrote each Lj as a linear combination of the s's, and we simply substitute this in. So in place of Lj, you get the sum from I equals 1 to m of Aij times Si. Now these are two finite sums, so it doesn't matter which order we add up the terms in. In particular, it's okay for us to swap the sums over and gather together the coefficients of SI. And when we do that, swapping those sums, the coefficient of SI becomes the sum from j equals 1 to n of aij times vj. But look what you've got in that bracket. What's in that bracket is the ith entry of AV. And AV is 0. So that bracketed term is equal to 0. In the next sum, we simply replace the bracketed term with 0. So we have a linear combination in which all the scalars are 0. And therefore we must have the 0 vector. Now that is a linear combination of the L's in which not every coefficient was 0 because V was a non-zero solution equal to the 0 vector. This contradicts L's linear independence, so it completes the proof. So to repeat what I said earlier, the important thing this result is telling you is that if you have a finite spanning sequence S1 up to Sm for a vector space, then it is greater than or equal to, its size is greater than or equal to the size of any linearly independent sequence in V. Spanning sequences are bigger than linearly independent sequences. Next, we're going to make another definition. A vector space is called finite dimensional if it has a finite spanning sequence. We've seen many examples. In fact, almost all the vector spaces we've seen so far were finite dimensional. So examples would include R to the n. The standard basis, which we've seen before, forms a finite spanning sequence. C to the n, similarly, its finite basis, its standard basis, forms a finite spanning sequence. And the spaces of matrices, m by n of R, or of C. Again, we've already seen finite spanning sequences for these, namely the standard bases we worked with. We've also looked at things like rings of polynomials of, or rather, vector spaces of polynomials of bounded degree, like R less than or equal to n of x, or C less than or equal to n of x. Those things had a finite spanning sequence, 1x, x squared, up to x to the n. So these are all examples of finite dimensional vector spaces. For short, we might write FDVS for finite dimensional vector space. On the other hand, we have seen some examples of vector spaces which are not finite dimensional. If you took all of the polynomials in one variable x with real coefficients, or if you took the same thing with complex coefficients, or if you took our vector space curly f, which you will remember consisted of all functions from the real numbers to the real numbers, those things are not finite dimensional. It's not easy to prove this, but we're not going to do this. Our focus in 0007 is purely on finite dimensional vector spaces. Now that we've done Steinitz exchange, we can prove quite easily the following result. It says that if V is a finite dimensional vector space, then if you have any two bases of V, they must have the same size. So first of all, let's note that any basis of V must actually be a finite sequence. V has a finite spanning sequence because it's a finite dimensional vector space, and that's the definition of being a finite dimensional vector space. So every linearly independent sequence must actually be finite, and that tells you every basis must be finite. Now, if you have two different bases, B and C, then on the one hand, B is a linearly independent set and C is a spanning sequence. Let me say that again. B is a linearly independent sequence and C is a spanning sequence. So Steinitz exchange tells you the size of B is less than or equal to the size of C. But then you can just play the same game the other way around. C is a linearly independent sequence and B is a spanning sequence. So the size of C is less than or equal to the size of B. So just by swapping the roles, we get the inequality the other way around, and that tells you that any two bases, even if they're different, must have the same size. So we're ready to make our definition, which is that if V is a finite dimensional vector space, the dimension of V, which we write like this, is the size of any basis of V. We now know that that definition makes sense because any two bases have the same size. We also make a special case in this definition. The definition of the zero vector space, so the vector space just containing a single vector, which is the zero vector for that space, is defined to be 0. But there are still issues with this definition. First of all, we don't yet know that every finite dimensional vector space even has a basis. There's not been any proof of this so far. Next, if the dimension is going to be a good measure of the size of a vector space, it ought to have some properties, such as that the dimension of a subspace ought to be less than or equal to the dimension of the space it was a subspace of. Otherwise, it wouldn't be a good measure of size at all. Next, we don't even know that a subspace of a finite dimensional vector space is again finite dimensional. A finite dimensional vector space has got a finite spanning sequence, but there's no reason that finite spanning sequence should belong to any given subspace. So there's even something to prove there. We're going to investigate these problems and solve them all in the next lecture.